the most powerful telescope man has ever made, 100 times more powerful than the Hubble Telescope, the James Webb Space Telescope, or JWST. Join us in a new era of space exploration. With the James Webb Space Telescope, we can reach parts of the universe we have never seen before and get a new perspective on the mysteries of the universe. In today's video, we're going to fully explain the science behind this stunning piece of engineering, the heart of the JWST. There is one major task for the JWST that its predecessor Hubble failed to do, and it is to examine the very early stages of the universe, to look into the first ever star and galaxy that have formed, to look beyond time, to know the true origins of the universe. The Integrated Science Instrument Module, ISIM, is the heart of the Webb Telescope, or what the engineers call the main payload. It houses the 4 main instruments that will detect light from distant stars and galaxies. How does the JWST achieve this? Well, the ISIM has 4 components, which are mainly infrared-related instruments: the near-infrared camera, NIRCam, near-infrared spectrograph, NIRSpec, mid-infrared instrument, MIRI, and lastly, the Fine Guidance Sensor, FGS. First, the near-infrared camera is the telescope's main feature, as it is the primary imager that covers the infrared wavelength range from 0.5 to 6 microns. Near-infrared is used because it has a longer wavelength that can reach farther into space and is less hindered by small dust particles, allowing it to seep through dust clouds. The Hubble telescope was not able to do this because it operated mainly in ultraviolet, which has a shorter wavelength. The NIRCam is equipped with chronographs, telescopic attachments designed to block out direct light from stars, which allow astronomers to take pictures of very faint objects in the universe around a central bright object, like stellar systems. The second ISIM component is the near-infrared spectrograph, or NIRSpec, which analyzes the spectrum of any object in space as it separates incoming light by its wavelength and frequency. It can help us understand the stellar object's physical properties and chemical composition. The atoms and molecules in the object actually imprint lines in the spectrum that uniquely fingerprint each chemical element present, which reveals a lot of information for scientists. The third part, the mid-infrared instrument, MIRI, has both a camera and a spectrograph on board, which can see broader regions with less detailed information. Hubble also had such an instrument and has taken some of Hubble's most breathtaking photographs of galaxies. Though MIRI is not as powerful as the NIRCam, just look at these images of the Southern Ring Nebula, which were captured in near-infrared and mid-infrared. The near-infrared image shows much more detail, as you can see more stars from the side of the nebula, while in mid-infrared it is dimmer and pale compared to the near-infrared. The last instrument inside ISIM is the Fine Guidance Sensor, or FGS. This instrument is equally important as the others because it serves as a guide for the telescope to point precisely at the object astronomers want to observe. It serves other functions as well. It also provides input about the observatory's attitude control system, or ACS, which controls the orientation of the aerospace vehicle and keeps it right on track. This ISIM is the heart of the telescope, but the JWST consists of much more. Keep watching as we're about to dig into JWST's golden mirrors, its power system, and its protective armor. The eyes of the JWST. While the ISIM is the heart of the telescope, the optical telescope element, OTE, serves as its eyes. One of its main features is the humongous golden-plated mirrors. Maybe you're wondering why a powerful telescope needs a large mirror. Webb will be observing galaxies that are very distant, at over 13 billion light-years from us. But there's a problem. If we want to see what happened right after the Big Bang, we need some kind of object that will gather the faintest light from these objects. And a very large mirror is well suited for this job. A telescope's sensitivity, or how much detail it can see, is directly related to the size of the mirror area that collects light from the objects that are being observed. Scientists and engineers determined that a 21-foot, 6.5-meter mirror is needed to measure light from distant galaxies. Building a mirror this big is challenging because as it gets bigger, it becomes susceptible on bending under its own weight. A mirror this big cannot fit into a rocket. So the next problem they faced was how to launch this into space. Well, the solution sounds easy: folding mirrors. A team of engineers created 18 separate folding mirrors with a hexagonal shape to fit inside the rocket, and they have unfolded right after the JWST was launched. These mirror segments are made of beryllium, which is a durable, light material. Each segment weighs around 46 pounds, 20 kilograms, and is plated with gold. So, why use a precious material like gold? Well, the gold plating optimizes the function of these mirrors. To put it into perspective, silver and aluminium mirrors here on Earth reflect 85 to 95% of infrared light, whereas gold reflects 99%, which makes it the most reflective metal on Earth. Alongside this massive mirror is a 2.5-foot, 0.74 meter second mirror, which catches the light that hits Webb's primary mirrors and passes it on to a third mirror. The third mirror will remove the telescope's astigmatism and will flatten the focal plane, making it ready to pass light to the scientific instruments. The OET also requires a spine that can hold almost 5,300 pounds, 2,400 kilograms of weight to support not just the mirrors, but also the entire module of scientific instruments. This amazing backbone can also withstand temperatures up to -400 degrees Fahrenheit or -240 degrees Celsius. To give it an unprecedented thermal performance in space, it is made up of advanced graphite composite materials combined with titanium. Now that we have the mirrors and the telescope in place, we just need some kind of vehicle and a way to keep it safe in space. The body and the brain of the JWST. The JWST spacecraft bus is its body and holds all the other accessories to make the telescope functional. It holds the electrical power subsystem, which includes solar panels that convert sunlight into energy to power the telescope. Then there's the communication subsystem, which receives instructions from the command center and submits back science and status data. The spacecraft bus also holds the propulsion subsystem, which contains fuel tanks and the rockets that are fired to maintain orbit. On top of that is the brain of the entire observatory, the command and data handling system. The system has a computer that takes in commands from the communication system and directs them to the appropriate recipient back on Earth. It also has a data storage device for the observatory. JWST's armor. The last and vital part for the telescope's survival through space is a massive sun shield that protects it from the vigorous sun rays that may damage the components of the telescope. Since the JWST is primarily observing infrared light, it must be kept extremely cold to detect faint heat signals. To protect the telescope from external heat sources, it has a 5-layer sun shield the same size as a tennis court that acts as a parasol and provides shade. The sun shield consists of 5 layers of material called kapton, a polyimide film used in flexible printed circuits and space blankets. It remains stable at the lowest temperatures and does not burn or melt at very high temperatures. Each successive layer of this shield is cooler than the one below. The heat radiates out from between the layers as the vacuum between them acts as an insulator. With all these components combined, the telescope is now complete. The dream of having a telescope that can reveal the origins of the universe is now in the palm of our hands. It is just a matter of time for this marvel of engineering to unravel the mysteries of the universe.